I want you to consider for a moment that the universe you observe on a clear, dark night is not an empty expanse or a cold void stretching infinitely in every direction. Instead, imagine it as something far more profound, a tremendous invisible canvas, an elastic material that fills all of existence, occupying every corner of space and extending through time itself. You can't touch or perceive this material, of course, but it is very real. Scientists refer to it as Spacetime. This is the stage upon which all cosmic events play out, where stars are born and perish, planets orbit, and galaxies collide. This fundamental fabric of our reality is not static. It possesses the ability to bend, stretch, and even ripple, much like the surface of a pond after a stone has been tossed in. These particular ripples, these waves that travel through the very structure of reality, are what we now know as gravitational waves. They are generated not by a stone, but by something of unimaginable mass moving at incredible speeds, the result of a truly catastrophic cosmic event. This could be the intricate dance of two colossal black holes spiraling inward before merging into a single monstrous entity. Or it could be the violent collision of neutron stars, the incredibly dense remnants of deceased suns. During such cosmic cataclysms, a staggering amount of energy is unleashed, a portion of which literally agitates space-time and creates waves that propagate across the cosmos at the speed of light. These waves are unique. They don't transport light or any familiar form of radiation. Instead, they carry fundamental information about gravity itself, detailing the motion of massive objects and the most extreme phenomena the universe can offer. They are like an echo of immense collisions, the sound of the most powerful cosmic events reaching us across the vastness of space and time. The notion that gravity could generate such waves originated from one of the most brilliant minds in history, Albert Einstein. Early in the 20th century, his general theory of relativity completely transformed our understanding of the universe. Prior to Einstein, gravity was seen as an enigmatic force that acted over great distances, as if the sun held its planets on invisible tethers. He offered a radical new perspective, proposing that gravity is not a force in the conventional sense, but is instead a direct consequence of the universe's own geometry. According to Einstein's model, massive objects like our sun don't exert a pull on other bodies. Instead, they warp and bend the fabric of space-time around them, similar to how a heavy bowling ball deforms a stretched rubber sheet. Less massive objects, such as planets and satellites, are simply following the straightest available path through this curved geometry, much like a marble rolling along the slope created by the heavier ball. It was from this revolutionary concept, that gravity is the curvature of space-time, that the prediction of gravitational waves naturally emerged. If a massive object can warp space-time, Einstein reasoned, then an accelerating object must create disturbances in that curvature that would propagate outward. For instance, two massive stars orbiting one another are constantly churning space-time, generating ripples that carry energy away from their system. Yet Einstein himself was acutely aware of how incredibly feeble these waves would be. Despite its power to bind entire galaxies, gravity is by far the weakest of nature's fundamental forces. To appreciate this, just think of how a simple refrigerator magnet can lift a paperclip, effortlessly defying the gravitational pull of the entire planet Earth. Because gravity is so weak, the waves it produces are almost infinitesimally small. By the time a gravitational wave from a distant cosmic event reaches our planet, it produces only a minuscule distortion of space. Even the merger of two black holes will only alter the distance between 2 points several kilometers apart by an amount thousands of times smaller than the nucleus of a single atom. This gives you some idea of the monumental challenge that confronted the scientists who set out to find these elusive signals. Consequently, although Einstein predicted their existence back in 1916, it required nearly 100 years for humanity to develop the technology capable of directly detecting them. It stands as one of the most formidable experimental hurdles in the history of science. Capturing this tremor in the universe is comparable to trying to hear a single whisper from across a storm-tossed ocean. The successful detection of gravitational waves has given us a completely new method for studying the cosmos, enabling us to listen to phenomena that remain invisible to traditional telescopes. It provides a direct window into the realm of extreme gravity, the universe of black holes and neutron stars, which is only now starting to unveil its secrets. The simple idea that the fabric of spacetime could ripple and vibrate like a liquid surface remains one of the most stunning and profound outcomes of Einstein's general theory of relativity, which he first presented to the world in 1915. While formulating the mathematical underpinnings of his theory, Einstein found that his equations yielded solutions resembling waves, much like those that describe how light and electromagnetic energy travel. The theory proposed that any massive object undergoing acceleration would generate disturbances in the surrounding gravitational field. These disturbances would then ripple outward in every direction at the speed of light, manifesting as gravitational waves. To help you visualize this, imagine taking a very heavy ball and shaking it or spinning it off-center. This action would create a constantly shifting curvature in the space-time around it. These changes can't spread across the universe instantly. They must travel at a finite velocity, similar to ripples expanding across the surface of water. These very ripples are gravitational waves, carrying with them both energy and information about what created them. Even after making this prediction, Einstein himself was deeply skeptical that these waves could ever be directly observed. This doubt was rooted in the profound weakness of the gravitational force itself. To generate gravitational waves with any measurable amplitude, you would need truly colossal masses moving at relativistic speeds, which are velocities approaching that of light. Even when considering the most powerful events imaginable in the cosmos, like binary star systems or the explosion of a supernova, the calculations were daunting. They showed that by the time these waves reached Earth, their effect, the subtle stretching and squeezing of space, would be so infinitesimally small that detecting it seemed utterly beyond the technology of his era, or even the conceivable future. For a period, Einstein even questioned their physical reality, going so far as to publish papers attempting to demonstrate they were merely a mathematical quirk of his theory. He later retracted this view and affirmed their genuine existence as a necessary consequence of his work. Nonetheless, the prediction had been made, and it stood as one of the most compelling yet unverified elements of his grand theory. For many decades, gravitational waves were confined to the domain of pure theory. Physicists debated their characteristics and calculated which astrophysical phenomena could produce them most effectively, but no one made a serious attempt to detect them experimentally. The challenge simply appeared too great to overcome. This landscape began to shift in the late 1950s and early 1960s, primarily due to the groundbreaking efforts of the American physicist Joseph Weber. Weber wasn't just a theorist. He was an audacious experimenter who dared to confront a challenge that seemed nearly impossible. He proceeded to design and construct the very first detectors for gravitational waves, which became known as Weber bars or resonant antennas. Picture a massive, solid aluminum cylinder, approximately 2 meters in length and 1 meter in diameter, weighing several tons and suspended inside a vacuum. Weber's hypothesis was that a passing gravitational wave of a particular frequency would induce mechanical vibrations in this cylinder, causing it to resonate faintly, much like a bell that has just been struck. The frequency of this resonance would need to align with the cylinder's own natural resonant frequency. To register these minuscule vibrations, Weber outfitted his cylinders with highly sensitive piezoelectric sensors, which could transform the slightest mechanical distortion into a detectable electrical signal. He set up these detectors at a great distance from one another, one located in Maryland and a second at Argonne National Laboratory near Chicago, to rule out local interference like earthquakes or passing vehicles. The core idea was that an authentic gravitational wave from a cosmic source would trigger simultaneous signals in both locations. In the late 1960s, Weber made a stunning announcement. He claimed to have recorded such concurrent signals, suggesting the potential detection of gravitational waves that he believed were originating from the center of our galaxy. This declaration sent a massive wave of excitement through the scientific world. Had the elusive waves predicted by Einstein finally been captured? Research teams across the globe quickly began constructing their own resonant detectors to confirm Weber's results. Unfortunately, to the disappointment of many, no other group was able to reliably replicate his observations. It eventually became clear that the sensitivity of Weber's detectors was probably not sufficient to register the faint signals expected from astrophysical events. His reported coincidences were likely the product of incorrect statistical analysis or unrecorded sources of noise. Although Weber's direct detection of gravitational waves was never validated, his work held immense importance. He effectively established an entirely new discipline, experimental gravitational wave astronomy. He proved that, while exceptionally difficult, the hunt for these waves was possible in principle, and in doing so, he catalyzed the creation of new technologies and theoretical approaches. Following the failure of the initial resonant detectors, several decades passed with few experimental advances. Gravitational waves once again took on the status of a sort of holy grail for physicists, a phenomenon predicted by a celebrated theory, but one that continued to evade direct observation. During this time, theorists worked to refine their models of cosmic sources, predicting the precise signal shapes from events like the merging of black holes and neutron stars. Meanwhile, experimentalists focused on improving the sensitivity of resonant detectors, cooling them to extremely low temperatures to minimize thermal interference, and started to explore fundamentally different methods, such as laser interferometry. For many years, however, this search produced no definitive results, and maintaining faith in eventual success demanded extraordinary persistence. Then, in the mid-1970s, an event occurred that provided the most powerful evidence for the existence of gravitational waves to date, even though it wasn't a direct detection. This discovery breathed new life into the search. In 1974, American radio astronomers Russell Hulse and Joseph Taylor, using the massive Arecibo radio telescope in Puerto Rico, found a remarkable celestial object. The binary pulsar known as PSR B1113+16. Pulsars are rapidly spinning neutron stars, the incredibly dense cores left behind after massive stars explode in a supernova. As they rotate, they emit focused beams of radio waves from their magnetic poles. If you can imagine a cosmic lighthouse, you'll have a good idea of how they appear to us from Earth. Because of their spin, these stellar objects send out beams that periodically sweep past our planet, much like a lighthouse, which we can register as perfectly regular radio pulses. The pulsar that Hulse-Taylor identified was not alone. It was part of a tightly bound binary system, orbiting another compact star that was invisible in the radio spectrum, but equally dense. This companion was later confirmed to be another neutron star. The extraordinary nature of this system was that two massive neutron stars were revolving around each other in a compact elliptical orbit, completing a full circle in just about 7.75 hours. This arrangement provided a perfect, natural laboratory for putting the predictions of general relativity concerning gravitational waves to the test. Einstein's theory stated that such a system, with two massive bodies orbiting at high speed and in close proximity, should radiate intense gravitational waves, which would drain energy from it. This loss of energy was predicted to make the stars gradually spiral inward toward each other, causing their orbital period to decrease over time. Using the incredible accuracy of the pulsar as a cosmic timepiece, Hulse-Taylor initiated decades of meticulous measurements of its pulse arrivals. They found precisely what general relativity foresaw. The system's orbital period was indeed shrinking, and the rate of this decay, approximately 76 microseconds per year, matched the theoretical calculations for energy loss from gravitational wave emissions with stunning precision. This discovery provided the first, deeply compelling, albeit indirect confirmation that gravitational waves were real. The behavior of the PSIR system aligned perfectly with what would happen if it were losing energy through the emissions Einstein's theory described. For this breakthrough, and its brilliant validation of general relativity, Hulse-Taylor received the Nobel Prize in Physics in 1993. Their work ultimately convinced the scientific community that gravitational waves were a genuine physical phenomenon with a tangible impact on the universe, not merely a theoretical construct. This finding acted as a powerful catalyst, driving the expansion of efforts to directly detect gravitational waves. It spurred the development and construction of enormous laser interferometers, which scientists hoped would finally allow them to directly hear these faint whispers from the cosmos. Following decades of investigation, a period that saw bold but unverified claims alongside encouraging indirect proof, like the Hulse-Taylor binary pulsar, it became clear that capturing these waves directly would demand entirely new instruments, vastly more sensitive than Weber's resonant bars. The century-long quest was nearing its culmination, heralding a new chapter in the hunt for spacetime ripples, the age of giant laser interferometers. While the concept behind these remarkable instruments is elegantly simple, its practical execution demanded engineering innovations that stretched the very limits of technology. This vision was brought to life by two flagship projects: the Laser Interferometer Gravitational-Wave Observatory, or LIGO, in the United States, and the Virgo detector near Pisa, Italy. They were later joined by the Kagra detector in Japan, forming a worldwide network for gravitational wave observation. Each of these L-shaped observatories features an exceptionally long and perfectly straight vacuum tunnel for each arm, extending for several kilometers, 4 kilometers in LIGO's case, and 3 for Virgo. A powerful and highly stable laser is positioned at the corner of the L, where the two tunnels intersect. A specialized beam splitter divides its light into two identical beams, sending one down each tunnel. At the far end of each arm, a flawlessly polished mirror is suspended. Once the laser beams strike these mirrors, they are reflected back toward the beam splitter, where they merge once more, and are directed to a photodetector, a device designed to measure the intensity of light. The crucial aspect of this setup is that the entire system is precisely calibrated, so that under normal circumstances, when no gravitational wave is present, the two returning laser beams cancel each other out through a process known as interference. It is as if the peak of one light wave aligns perfectly with the valley of another, creating near total darkness at the detector. But imagine what occurs when a gravitational wave travels through the detector. As you know, such a wave produces a unique distortion of space, compressing it in one direction while simultaneously stretching it in the perpendicular direction. If a wave were to come from above, for instance, it could momentarily shorten one interferometer arm by an infinitesimal amount, while slightly lengthening the other. This alteration is incredibly small, thousands of times smaller than the diameter of an atom's nucleus. Even so, this tiny disturbance is sufficient to break the perfect cancellation of the light waves. The beam in one arm now covers a slightly shorter distance, while the beam in the other travels a fractionally longer path, meaning their peaks and valleys no longer align perfectly. Consequently, instead of darkness, a faint signal of light emerges at the photodetector. By tracking the changes in this signal's brightness over time, scientists can map the passing gravitational wave's shape, its unique melody. This is precisely why these instruments are known as laser interferometers. They employ the interference of laser light to gauge the most minuscule variations in distance. Naturally, the principle I've outlined is merely the surface level. Constructing such a device required solving immense technical puzzles, chief among them being the attainment of unbelievable sensitivity and the elimination of all conceivable sources of noise that might imitate the signal of a gravitational wave. Just think. The objective is to measure a change in a 4-kilometer arm's length by a magnitude on the order of 10 to the negative 19th power meters. Imagine trying to measure the distance to Proxima Centauri, our nearest stellar neighbor at 4 light-years away, with an accuracy equivalent to the width of a human hair. Any stray vibration could easily be misinterpreted as a signal. The sources of this background noise are virtually endless, ranging from Earth's seismic activity and distant ocean waves crashing on shores thousands of kilometers away, to the rumble of passing traffic, acoustic disturbances, and even the thermal agitation of individual atoms within the mirrors themselves. To overcome these challenges, engineers deployed an entire arsenal of brilliant solutions. The interferometer's mirrors are far from ordinary glass. They are incredibly sophisticated optical instruments, crafted to near-perfect precision. They are suspended by multi-stage seismic isolation systems designed to dampen terrestrial vibrations by a factor of millions, with the entire assembly acting as a complex pendulum that filters out external movements. Furthermore, the tunnels housing the laser beams are evacuated to an ultra-high vacuum, one of the most extreme ever created by humans in such a large volume. This measure is critical to prevent the laser light from scattering off stray air molecules, which would introduce fluctuations into its path. The lasers themselves must exhibit extraordinary stability in both their power output and frequency, as any variation could mimic the very gravitational wave signal the scientists are searching for. To amplify the detector's sensitivity, Additional mirrors are positioned in each arm between the main ones, forming what are known as Fabry-Perot resonators. Within these cavities, the light bounces back and forth hundreds of times before it recombines at the beam splitter. This technique effectively multiplies the length of the arms by several hundred times, dramatically increasing the instrument's ability to detect minuscule changes in distance. Bringing these incredible detectors to life was a monumental undertaking that spanned decades, involving thousands of scientists and engineers, substantial financial investment, and a steadfast belief in its ultimate success. The Laser Interferometer Gravitational-Wave Observatory, or LIGO, is composed of two identical detectors situated approximately 3,000 kilometers apart, one in Hanford, Washington, and the other in Livingston, Louisiana. This configuration allows researchers to differentiate a genuine cosmic event from localized noise, as a true gravitational wave will register at both sites with a slight delay, while interference would likely appear at only one. The inclusion of a third detector, Virgo in Europe, and later Kagra in Japan, not only bolsters the confidence in any detection, but also enables scientists to triangulate the source's position in the sky. After extensive years of fine-tuning and progressive enhancements to their sensitivity, the upgraded advanced LIGO detectors were poised to commence a new observation run in the autumn of 2015. It was then that something truly remarkable happened. On September 14, 2015, just days before the official start of the scientific program, both LIGO facilities simultaneously recorded a powerful and unambiguous signal during final calibration tests. The signal manifested as a distinctive chirp in the data that lasted for only a fraction of a second, immediately triggering alerts from the analysis systems. When researchers inspected the signal's shape, they were absolutely astonished by what they saw. The signal possessed a characteristic upward sweep in frequency, its purity and amplitude growing smoothly before it abruptly ceased. This was the exact signature that general relativity had predicted for the final, violent moments of a black hole merger. The event originated from the collision of two black holes, with masses around 36 and 29 times that of the Sun, which occurred approximately 1.3 billion light-years from our planet. In the final moments before they combined, these celestial behemoths were circling each other at nearly half the speed of light, generating potent gravitational waves. At the instant of their merger, a single, more massive black hole was formed, weighing in at about 62 solar masses. An immense quantity of energy, equivalent to the mass of 3 suns, was unleashed into the cosmos as gravitational waves in just a fraction of a second. The peak power of this gravitational wave burst was so immense that it momentarily outshone the combined luminosity of all the stars in the entire observable universe. This echo of a cosmic cataclysm, which had traveled for over 1 billion years, was finally intercepted on Earth, thanks to the extraordinary sensitivity of the LIGO detectors. After meticulously excluding all conceivable instrumental artifacts and sources of noise, the scientific teams from the LIGO and Virgo collaborations were certain. They had made a historic discovery. This was the first direct detection of gravitational waves, realized almost exactly 100 years after Albert Einstein had first theorized their existence. The groundbreaking news was kept a closely guarded secret for several months during the preparation of the scientific paper. When the official announcement was finally made on February 11, 2016, it sent shockwaves through the scientific world and ignited widespread public fascination, marking a triumph of human intellect, engineering ingenuity, and scientific persistence. LIGO and Virgo accomplished more than just confirming one of Einstein's most profound predictions. They opened up an entirely new way of observing the universe. They have given us the ability to hear the grandest and most hidden cosmic events, those which remain invisible to traditional telescopes. The miracle had finally occurred. The elusive ripple in spacetime had been captured, proving that the universe is filled with more than just the light of stars and galaxies. Imagine the cosmos resonating with invisible sounds, the powerful vibrations of the very fabric of spacetime. These gravitational waves are born from the most violent and catastrophic events imaginable, where immense masses move at incredible speeds and monstrous gravity twists space and time into knots. Thanks to astounding detectors like LIGO and Virgo, we have finally developed the ears necessary to listen to this cosmic symphony, and what we have heard so far has surpassed all expectations. What other cosmic events serve as the universe's giant drums or violins, whose vibrations can reach us across billions of light years? Among the most distinct and powerful signals we can now perceive from the cosmos are those marking the cataclysmic final moments of two colliding black holes. You may know black holes as the universe's most enigmatic objects, zones in spacetime with gravity so immense that nothing, including light itself, can break free. These phenomena arise from the collapse of exceptionally massive stars. It's quite common for two such stars, born as a pair, to conclude their dramatic lives by collapsing into black holes that remain gravitationally tethered, destined to orbit a shared center of mass in a silent cosmic ballet. Albert Einstein's general theory of relativity predicts that a system of two massive objects orbiting each other in this way must constantly radiate gravitational waves. This emission steadily saps energy from the pair, forcing the black holes into a slow but certain spiral toward one another. As they draw closer, their orbital dance quickens, eventually reaching velocities that are a significant fraction of the speed of light. In the final sliver of a second before they unite, they circle each other hundreds of times per second, a frantic rotation that unleashes the most intense gravitational waves imaginable, which then propagate across the universe. The amplitude and frequency of these waves build up as the black holes approach their merger, creating a distinctive signal known as a chirp, which was famously detected for the first time on September 14, 2015, in an event catalogued as GW150914. Ultimately, the boundaries of the two black holes, their event horizons, make contact, and they combine into a single, larger black hole that is initially distorted and vibrating. This newly formed object rapidly settles into a stable state by releasing its excess energy as a final burst of gravitational waves in a process called the ring-down, which resembles the fading hum of a struck bell. The complete gravitational wave signature, from the last few orbits to the final settling of the new black hole, encodes rich information about the masses and spins of the original objects and the properties of the final one. The very first confirmed event, GW150914, was truly stunning. It came from the merger of two black holes weighing approximately 36 and 29 times the mass of our Sun. This was a revelation, as scientists hadn't expected stellar mass black holes to be so heavy, nor did they realize such mergers were a relatively frequent cosmic occurrence. Since then, the LIGO and Virgo observatories have catalogued dozens of similar events, unveiling an entire cosmic population of binary black holes we had previously only theorized about. However, black holes are not the sole actors in this cosmic theater. The collision of neutron stars has been identified as another potent source of gravitational waves. Neutron stars represent a different kind of incredibly dense remnant left behind by massive stars, though they fall short of the density required to form a black hole. While containing a mass comparable to or slightly greater than the Sun's, their diameter spans a mere 10 to 20 kilometers. The matter within is so compressed that electrons are crushed into protons, creating a sea of neutrons, where a single teaspoonful of this material would weigh billions of tons on Earth. Much like black holes, neutron stars can exist in binary systems, circling one another in a gravitational embrace. And just as with black holes, the continuous emission of gravitational waves causes them to lose energy and gradually spiral inward. Their eventual collision, however, is an event of staggering power and intricacy. When two neutron stars smash into each other at nearly the speed of light, the result is a gargantuan explosion. In stark contrast to black hole mergers, which occur in total darkness, a neutron-star merger ignites a spectacular display of electromagnetic radiation across the entire spectrum, from gamma rays and X-rays to visible light and radio waves. At the instant of impact, a portion of the ultra-dense, neutron-rich material is violently flung outward. Within this searing ejecta, unique nuclear reactions known as the R process, or rapid neutron capture process, take place. It is during this process that the universe forges its heaviest elements, including gold, platinum, and uranium. For a very long time, astronomers had speculated about the cosmic origins of these precious materials. On August 17, 2017, a landmark event provided definitive proof. The LIGO and Virgo detectors captured a gravitational wave signal, designated GW170817, which differed from the black hole signals. It was longer, and corresponded to the merger of objects with much lower masses, around 1.1 and 1.6 times that of the Sun, which is typical for neutron stars. Critically, just 2 seconds after the gravitational waves arrived, the Fermi Space Telescope detected a short gamma-ray burst from the exact same patch of sky. This marked the first time in history that a single astronomical event was witnessed through both gravitational waves and light. In the following days and weeks, observatories worldwide focused on the location provided by LIGO and Virgo, discovering a new point of light, a kilonova, the radiant afterglow of the neutron-star collision. A spectral analysis of this light confirmed the presence of freshly created heavy elements, such as strontium, and very likely gold and platinum as well. The GW170817 event was a crowning achievement for what is known as multi-messenger astronomy. This field, which combines data from different cosmic messengers like light, gravitational waves, and neutrinos, has now powerfully shown that neutron-star mergers are indeed a primary cosmic factory for the universe's heavy elements. While the mergers of black holes and neutron stars are the sources of gravitational waves we can most reliably detect today, theoretical physics predicts other potential origins. Scientists are hopeful that as detector technologies become more sensitive, or with the advent of next-generation instruments, you and I will be able to discover these other cosmic whispers as well. One potential origin for these waves is the explosion of supernovae, which marks the final, violent demise of massive stars as their cores implode and their outer shells are blasted into space. Because this core collapse and the subsequent detonation are probably not perfectly uniform, the asymmetrical high-speed motion of such immense mass should produce gravitational waves. While the resulting signal would be far more complex and weaker than those from merging compact objects, its detection would offer priceless insights into the mechanics of supernova events, which are still not fully understood. Another possible source lies in rapidly rotating neutron stars, known as pulsars. A neutron star would not release gravitational waves if it were a perfect sphere, no matter how fast it spun. However, if its surface has slight imperfections, so-called mountains that are only centimeters or meters tall but incredibly dense, or if its spin axis is misaligned with its symmetrical axis, its rotation would create continuous, single-frequency gravitational waves. These signals are exceptionally faint but constant, giving scientists hope that they can be identified through the gradual accumulation of data over long periods. Perhaps the most thrilling, and certainly the most difficult objective, is to find primordial gravitational waves, which are essentially echoes from the Big Bang. Certain cosmological theories suggest that in the universe's earliest moments, quantum jitters in space-time were stretched to cosmic proportions during the inflationary era of swift expansion. These ancient ripples should now fill all of space as a gravitational wave background. Capturing this primordial signal would offer direct proof of inflation and let us gaze into the most ancient epoch of our universe, far earlier than what the cosmic microwave background can show us. Ultimately, gravitational waves give you a way to access the most extreme and energetic phenomena in the cosmos. They enable you to listen to black hole collisions that happen in total darkness, witness the creation of heavy elements as neutron stars merge, and they offer the possibility of solving the puzzles of both supernovae and the birth of the universe. The cosmic symphony is only just beginning for us, and its most incredible compositions surely lie ahead. The detection of gravitational waves wasn't just another milestone for science, or a simple validation of Einstein's genius. It was the dawn of a completely new method for comprehending the cosmos. For thousands of years, our entire knowledge of distant stars, planets, and galaxies was derived from light. The full spectrum of electromagnetic radiation, from radio waves to gamma rays. Conventional astronomy is founded on capturing and interpreting these photons as they arrive from the far reaches of space. It's as if we have been studying the world using only our sense of sight. But imagine if you could also hear. Gravitational waves represent this new cosmic sense, as they are not a form of light, but an entirely different kind of signal that carries information about moving masses and the fabric of space-time itself. This fundamental distinction provides gravitational wave astronomy with some unique strengths. Even the most powerful light can be absorbed or scattered by the vast clouds of interstellar dust and gas that fill galaxies, hiding many fascinating objects and events from our view. For instance, the center of our own Milky Way galaxy, home to a supermassive black hole, is almost completely obscured in visible light by these dense dust clouds. Although we can probe it using radio or infrared waves that better pierce the haze, the information we get is still restricted. Gravitational waves, by contrast, have an incredibly weak interaction with matter, making them virtually unstoppable. For them, dust and gas clouds are completely transparent. They travel through planets, stars, and entire galaxies without being distorted, delivering pristine information about their source, even if it is located in the heart of a dense galaxy or concealed by thick material layers. This ability allows you to peer into regions of the universe and observe phenomena that would be utterly invisible to any light-based telescope, such as the merger of two black holes, an event that generates no light whatsoever. By adding to the picture of the universe we get from light, gravitational waves give you an entirely fresh perspective and a way to investigate the universe's dark side, including phenomena governed by extreme gravity. But their importance goes beyond just uncovering what is hidden. They also serve as a unique instrument for testing the fundamental principles of physics, especially Albert Einstein's general theory of relativity, in the most extreme environments the universe has to offer. The theory provides a magnificent description of gravity within the relatively gentle fields of our solar system, and its predictions have been confirmed with remarkable accuracy time and again. However, the real question is how the theory holds up where gravity becomes truly colossal. In the vicinity of black holes and neutron stars, where spacetime is warped to its limit and matter moves at nearly the speed of light. It is in this arena, during the mergers of such compact objects, that the general theory of relativity undergoes its most rigorous examination. The signals from these events allow you to observe precisely how spacetime behaves when pushed to its breaking point, offering the ultimate test of our understanding of gravity. By meticulously examining the unique signature of a gravitational wave signal, from the rising pitch of the in-spiral chirp to the climactic merger and the final calming ring down, scientists can put the most detailed predictions of Einstein's equations to the test. So far, general relativity has passed every one of these trials with stunning accuracy in all observed events. This flawless agreement between theory and observation not only reinforces our confidence in it as the fundamental theory of gravity, but also severely restricts any potential alternative theories that might deviate in strong gravitational fields. Gravitational waves have thus emerged as a potent new tool for directly studying black holes and neutron stars, objects that had long been confined primarily to theoretical speculation. By analyzing the signals from their mergers, we have begun to take what you might call a cosmic census of these exotic bodies. We can now measure their masses, and these measurements have already delivered some profound surprises, challenging what we thought we knew. The very first detected event, GW150914, revealed the collision of black holes with masses around 36 and 29 times that of our Sun. This discovery astonished astrophysicists, as it was widely believed that stellar mass black holes in our galaxy typically topped out at 15 to 20 solar masses. Subsequent observations have since confirmed the existence of a whole population of these heavier black holes, compelling us to revise our models of massive star evolution, especially in low metallicity environments where stars retain more of their mass throughout their lives. Furthermore, we have detected events involving black holes that occupy the so-called upper mass gap, which spans roughly 50 to 130 solar masses. Certain theories predict that black holes in this range should not form directly from stars, due to pair instability effects during supernova explosions. The discovery of such objects, therefore, presents a fresh puzzle regarding their origins, with a leading hypothesis suggesting they are the products of previous black hole mergers. In addition to mass, gravitational waves enable us to measure the spin, or intrinsic rotation, of the black holes before they combine, as well as the properties of the final merged black hole. This information offers you crucial insights into how these binary systems formed, and the physics of the merger process itself. It has also become apparent that these events are much more common than once imagined. The LIGO and Virgo detectors now register them on average every few days or weeks, indicating that binary black holes and neutron stars are plentiful in the cosmos. Perhaps one of the most significant triumphs of gravitational wave astronomy has been confirming the role of neutron star mergers in creating the universe's heavy elements. The historic GW-170817 event, which gave us our first ever simultaneous observation of both gravitational waves and electromagnetic light from a kilonova, represented a monumental breakthrough. For decades, the source of elements heavier than iron, like gold, platinum, and uranium, remained an unresolved question, with neutron star collisions being a primary suspect for creating the extreme conditions required for the rapid neutron capture process, or R process. The observations of the kilonova that followed GW-170817 and the analysis of its spectrum revealing the presence of newly forged heavy elements provided conclusive proof for this hypothesis. This means that much, if not all, of the gold and platinum in your jewelry, the uranium in nuclear reactors, and many other rare and heavy elements were forged in the titanic collisions of neutron stars that took place billions of years ago. These materials were then scattered across the cosmos, eventually becoming part of new stars and planets, including our own Earth. An amazing realization of your direct connection to the universe's most catastrophic events. Finally, gravitational waves are opening new windows into cosmology, the science of the universe as a whole, including its origin, evolution, and large-scale structure. One of the foremost goals in modern cosmology is the precise measurement of the universe's current rate of expansion, a value known as the Hubble constant, or H0. There is a significant challenge, however, as the two primary methods for measuring it, one based on the cosmic microwave background and the other on standard candles like Type 1a supernovae, yield conflicting results. This disagreement, known as the Hubble tension, is one of the major puzzles in cosmology today, and could point to fundamental gaps in our understanding of the universe. Gravitational waves from merging objects, especially when accompanied by electromagnetic signals as in the case of GW-170817, provide a completely independent way to measure the Hubble constant. These events, called standard sirens, allow for a fairly precise distance determination from the gravitational wave signal alone. If you can then identify the host galaxy and measure its redshift, you can calculate the Hubble constant directly. And early results from this method have already produced a value that lies between those from the other two techniques. With the accumulation of data from new standard sirens, the accuracy of this gravitational wave approach is set to improve, potentially playing a decisive role in resolving the Hubble tension and refining our grasp of the universe's expansion. You see, gravitational waves are far more than just an exotic curiosity. They represent a formidable tool that is already reshaping our understanding of the cosmos. This allows us to perceive the invisible, to test nature's fundamental laws under the most extreme conditions, and to probe the origins of the chemical elements that compose our world, all while measuring the parameters of the universe itself. We are truly at the very beginning of a revolutionary age in astronomy, where we can only begin to guess what other incredible discoveries await as our ability to listen to the grand cosmic symphony improves. The initial detections by the Laser Interferometer Gravitational-Wave Observatory, or LIGO, and Virgo were just the first tentative notes, and researchers worldwide are now designing next-generation instruments to capture this symphony in its full glory. As remarkable as they are, today's detectors are constrained by their sensitivity and the frequency range in which they can perceive the universe, compelling us to develop more advanced cosmic ears. To peer deeper into the cosmos, capture faint signals from more distant events, and detect gravitational waves on an almost constant basis, projects for next-generation observatories are already underway, such as the Einstein Telescope, or ET, in Europe, and the Cosmic Explorer, or CE, in the United States. These facilities will be structures on a truly monumental scale. Imagine, not the L-shaped designs of LIGO and Virgo, but immense underground triangles with sides measuring 10 kilometers for ET and an incredible 40 kilometers for CE. Placing these observatories underground will drastically reduce seismic noise, a primary source of interference for existing detectors. By implementing cryogenic technologies to cool the mirrors to extremely low temperatures and utilizing more powerful lasers with advanced optics, these new instruments will be about 10 times more sensitive than the current advanced LIGO and Virgo installations. This tenfold increase in sensitivity will empower us to detect gravitational waves from merging black holes and neutron stars across a vastly expanded volume of space, effectively encompassing the entire observable universe. We will be capable of registering events that took place at the dawn of star and galaxy formation, offering priceless insights into the universe's early evolution. Furthermore, the number of recorded events is expected to surge dramatically, possibly reaching several mergers each day, which will enable us to compile vast statistical data to meticulously study the populations and properties of black holes and neutron stars. This heightened precision will also permit even more rigorous examinations of general relativity in extreme environments, potentially uncovering slight deviations that could signal the presence of new physics. These advanced detectors might also capture weaker signals, such as continuous gravitational waves from rotating neutron stars, or the elusive primordial gravitational background from the Big Bang itself. However, even these colossal ground-based facilities have inherent limitations, as they are unable to effectively detect gravitational waves at very low frequencies, specifically below a few hertz. The primary obstacles are unavoidable seismic interference from the Earth and gravitational fluctuations generated by the movement of the atmosphere and underground water. It is precisely within this low-frequency spectrum that we expect to find signals from the most magnificent events in the cosmos, such as the mergers of the supermassive black holes that reside at the centers of most galaxies, including our own Milky Way. To hear these ultra-low notes of the cosmic symphony, we must move the detector into space, far from terrestrial interference, and construct an interferometer of truly cosmic proportions. This is the objective of the ambitious Laser Interferometer Space Antenna, known as LISA, a joint mission between the European Space Agency and NASA. When galaxies collide, these cosmic behemoths, with masses millions or even billions of times greater than our Sun, produce gravitational waves with periods that can range from seconds to hours. LISA will be composed of 3 identical spacecraft that will orbit the Sun, trailing behind the Earth. In space, these craft will form a gigantic equilateral triangle, with each side stretching an incredible 2.5 million kilometers. Within each spacecraft, a test cube made of a gold-platinum alloy will float freely, shielded from all external forces like the solar wind and light pressure. Laser beams exchanged between the spacecraft will precisely measure the travel time, allowing for the detection of the slightest changes in distance between these test masses caused by a passing low-frequency gravitational wave. This mission will unveil an entirely new gravitational wave frequency range for observation, from 0.1 MHz to 1 Hz, which is completely inaccessible to ground-based observatories. LISA's main objectives will be the mergers of supermassive black holes across the universe, enabling us to trace their growth and their influence on the evolution of galaxies. It will also identify thousands of binary systems of compact stars in our own galaxy, many of which will continuously emit gravitational waves, generating a persistent gravitational wave hum that will provide a new map of the Milky Way. Another fascinating phenomenon to explore involves extreme mass ratio in spirals, also known as EMRIs. These events occur when an object with the mass of a star, like a black hole or neutron star, is drawn into a spiral towards a supermassive black hole at a galaxy's core. Such an in-spiral can unfold over many years, emitting gravitational waves that contain exclusive data about the spacetime geometry near the supermassive black hole, which allows for its mapping with exceptional precision and for testing general relativity in ways never before possible. The Laser Interferometer Space Antenna, or LISA, will also be tuned to a potential background of primordial gravitational waves originating from the very first moments of existence. These ancient ripples could have been generated by cosmic phase transitions or by hypothetical flaws in spacetime called cosmic strings. Yet, this is not the full extent of what you can detect. There are gravitational waves with even lower frequencies and periods lasting years or decades, existing within the nanohertz spectrum. These particular waves are thought to originate from the slow orbits of supermassive black hole pairs located at the centers of merging galaxies, long before they eventually combine. It's impossible to detect such incredibly long waves using interferometers, but astronomers have devised another brilliant approach. Employing a network of pulsars called pulsar timing arrays, or PTAs. These arrays utilize millisecond pulsars, which spin hundreds of times per second and serve as extraordinarily stable cosmic timekeepers. Pulsars emit radio pulses with strict periodicity, and by monitoring dozens of them across our galaxy with immense precision over many years, scientists aim to spot minute, correlated shifts in their pulse arrival times. A passing, ultra-low-frequency gravitational wave subtly stretches and compresses the space between Earth and a pulsar, making its signals arrive a fraction earlier or later than anticipated. Through the analysis of these timing variations across numerous pulsars, a shared signal from the gravitational wave background can be extracted. Recently, international collaborations like NanoGrav and the European Pulsar Timing Array have presented compelling proof of this nanohertz gravitational wave background. The most probable source is a vast population of binary supermassive black holes scattered throughout the universe. This represents another groundbreaking discovery, offering you a new perspective on the universe's most massive objects and how they evolve over time. The future of gravitational wave astronomy is therefore incredibly promising. We are not only preparing to deploy a colossal observatory in space, but are also learning to use the stars themselves as detectors, all in an effort to listen to the broadest possible range of the universe's cosmic sounds. However, the most significant emerging trend is arguably the growth of multi-messenger astronomy. The neutron star merger designated GW170817 offered a powerful demonstration of the priceless information you can acquire by observing a single event through multiple channels. In that case, both gravitational waves and light. In the years to come, this pair will increasingly be joined by neutrinos, the elusive particles produced in high-energy nuclear reactions, and by ultra-high-energy cosmic rays. Imagine having the ability to simultaneously witness the light from a supernova, detect the gravitational waves from its collapsing core, and capture the neutrinos escaping from the heart of the cataclysm. Fusing these signals provides the most thorough and detailed portrait of the event, an understanding that would be impossible to achieve through any single information channel alone. This effort demands tight collaboration between observatories on Earth and in space, along with rapid alert systems that allow telescopes to quickly pivot toward regions identified by gravitational-wave or neutrino detectors. The age of multi-messenger astronomy has already dawned, and its development promises to revolutionize our comprehension of the most extreme cosmic phenomena, from exploding stars to the engines that power active galactic nuclei. We can state with certainty that gravitational-wave astronomy is more than just a new scientific discipline. It's the gateway to a completely new level of understanding the cosmos. We have only just started to discern the universe's first sounds, with an entire symphony of discoveries still ahead. Future instruments will enable you to gaze into the most obscure corners of space, follow the evolution of galaxies and black holes across cosmic history, and maybe even perceive the echo of the Big Bang itself. We have effectively developed a new sensory organ for experiencing reality, and it's impossible to know what incredible secrets the universe will share with us as we refine our ability to listen. The influence of these women's contributions is felt far beyond their specific accomplishments, as their work has motivated subsequent generations of scientists and underscored the value of diversity in scientific fields. Today, women in astrophysics are at the forefront of groundbreaking research, encouraging others to investigate the cosmos and guaranteeing that their legacy will persist for centuries to come. Their discoveries challenge you to look more deeply into the universe, reminding us that its mysteries are best solved when the widest possible range of voices participates in the conversation. The invention of the telescope marked a pivotal moment in our perception of the universe, opening a window to the cosmos that had never before been available. Prior to this, your view was restricted to what the naked eye could see, and your understanding of the heavens remained largely tethered to Earth. With the emergence of telescopes in the early 17th century, celestial objects were revealed not as simple points of light, but as complex and dynamic worlds. One of the earliest champions of the telescope was Galileo Galilei. With an instrument he constructed himself, he observed the moons of Jupiter and showed that not every object in the sky revolves around the Earth. This crucial observation directly contested the long-standing geocentric model, which placed our world at the center of everything. Galileo's findings laid the groundwork for a new conception of our place in the cosmos, revealing it to be vastly more intricate than anyone had previously imagined. As optical instruments were refined over the centuries, our perception of the universe's immense scale expanded dramatically. The finer features of planets, the architecture of galaxies, and the dynamics of faraway stars came into sharper focus. Advancements in telescope technology unveiled marvels like the radiant rings of Saturn, the scarred surface of the Moon, and the swirling arms of distant galaxies. Each more powerful generation of telescopes uncovered celestial phenomena such as nebulae and supernovae, which profoundly deepened our comprehension of how stars are born and die. These technological leaps forward empowered astronomers to ask more profound questions regarding the fundamental nature of the cosmos, paving the way for investigations into dark matter, dark energy, and the very structure of spacetime. Instruments like the Hubble Space Telescope grant us the ability to gaze across billions of light-years into the cosmic abyss, radically altering our perspective on the universe. Telescopes continue to be essential instruments, enabling us to investigate and evaluate the universe's enigmas in ways that were previously confined to the realm of imagination. Carl Sagan stands as a monumental figure in science, celebrated for his talent in conveying intricate concepts in a manner that enchanted the public. Among his greatest achievements was making cosmic anomalies, from black holes and quasars to the strange behaviors of remote celestial objects, accessible to everyone. Through his 1980 television series, Cosmos, Sagan guided audiences on a journey to these wonders, pairing breathtaking visuals with clear, understandable explanations, which cultivated a widespread sense of awe and stimulated curiosity about the mysteries beyond our world. Sagan frequently employed striking analogies to make scientific principles more approachable, such as likening the bending of light near a black hole to water swirling down a drain, which helped viewers grasp an otherwise abstract idea. His approach did more than just educate. It motivated a whole generation to contemplate the universe and our role in it more deeply. His writings further popularized cosmic curiosities by merging scientific instruction with philosophical reflection, prompting readers to reflect on the universe's magnificence alongside the precariousness of human existence. By masterfully weaving scientific facts into compelling narratives, Carl Sagan forged an emotional connection with his audience, compelling them to think about how cosmic anomalies contribute to the greater cosmic narrative. The passion with which he communicated was as crucial as the information he shared, and his legacy endures through the inquisitiveness he sparked in millions. He succeeded in transforming the study of cosmic anomalies from a niche academic field into a subject of broad public fascination, helping to build a culture of scientific exploration that continues to flourish. The space race, a defining period that stretched from the late 1950s to the early 1970s, had a transformative effect on our grasp of cosmic phenomena. This intense competition, mainly between the United States and the Soviet Union, was fueled by a mutual ambition to achieve landmark successes in space exploration. This rivalry drove both nations to invest enormous resources into new technology and scientific research, which in turn spurred unprecedented innovation and helped unravel many of the universe's secrets. During this era, vast resources were channeled into creating satellite technology, which gave scientists powerful new tools to observe celestial events as never before. The launch of Sputnik, the first artificial satellite, in 1957, provided fresh data on cosmic radiation and the Earth's magnetosphere. This competitive drive also accelerated the development of sophisticated instruments like the Hubble Space Telescope, which vastly improved our capacity to study cosmic anomalies such as black holes and pulsars, ultimately enriching our cosmic understanding. While rooted in rivalry, the intense focus on space research also paved the way for international cooperation, as it became clear that the challenges were too great for any single nation to tackle alone. Collaborative efforts like the International Space Station united scientists and engineers from across the globe, enabling them to pool their knowledge and accelerate discoveries related to dark matter and the cosmic microwave background radiation. The space race ultimately laid the foundation for countless modern advancements, allowing us to decipher the cosmos's complexities and appreciate the anomalies that continue to challenge our view of reality. Ancient cultures provided foundational insights into our knowledge of the stars, their efforts often driven by practical needs, spiritual convictions, and the challenge of navigating their world. Civilizations like the Babylonians, Egyptians, and Greeks carefully tracked celestial movements, establishing the groundwork for early astronomy. The Babylonians, for instance, compiled extensive records of celestial events, which became a vital resource for the later development of Greek and Western astronomical models. The Egyptians, meanwhile, wove their stellar observations into their mythology and architecture, aligning their great pyramids with constellations and worshipping stars they believed were manifestations of their gods. An excellent example of this is the star Sirius, whose appearance was linked to the annual life-giving flood of the Nile River, a critical event for their agriculture. Their creation of a sophisticated solar calendar, based on a year of 365 days, showcases their remarkable skill in observing astronomical cycles. These early efforts were not just rudimentary observations, but systematic studies that formed the bedrock upon which all subsequent astronomical knowledge has been built, demonstrating a profound connection between the heavens and human civilization. The Maya people also demonstrated remarkable expertise in astronomy, creating a calendar system that masterfully wove together celestial movements and their spiritual convictions. You can see their focus on the planet Venus, linking its appearances to warfare and agriculture, which enabled them to schedule significant events with extraordinary astronomical precision. These ancient civilizations didn't just broaden their own comprehension of the cosmos. They also laid a foundation that continues to influence modern astronomy, leaving a legacy that stands as a tribute to human curiosity and our timeless quest to understand the universe. Throughout the history of humanity's journey into space, you'll find that several key missions have dramatically broadened our knowledge of faraway planets, revealing new enigmas within our solar system and beyond. Among the most distinguished is the Voyager program from the National Aeronautics and Space Administration, or NASA, which began in the late 1970s. The twin probes, Voyager 1 and 2, performed flybys of Jupiter, Saturn, Uranus, and Neptune, transmitting back astonishing images and priceless data that reshaped our perspective on the complex dynamics of these giant worlds and their systems. Another revolutionary endeavor was the Galileo mission, which was launched in the late 1980s with the specific purpose of studying Jupiter and its extensive collection of moons. Galileo delivered a wealth of information, not only on the gas giant itself, but also on its captivating satellites, including Europa, which is thought to conceal a vast ocean beneath its icy surface. These discoveries ignited discussions about the possibility of life existing beyond our planet, as Europa might possess the very conditions necessary to support it. Following in the wake of these pioneering missions, NASA's Mars rovers, Spirit, Opportunity, and Curiosity, have entirely reshaped our perception of the red planet. Equipped to perform direct observations and on-site analysis, these robotic explorers have supplied indispensable data regarding Mars's geological history and the potential for past water. Curiosity's detection of organic molecules further suggests that ancient life could have once existed there, positioning these missions as crucial instruments in our efforts to comprehend our planetary neighbor. More recently, the Juno mission, which has been in orbit around Jupiter since 2016, continues to make headlines with its sophisticated instruments. It is meticulously mapping the planet's gravitational and magnetic fields, unveiling the underlying structure of its atmosphere, and examining its intricate weather patterns. Every one of these missions adds another vital piece to the cosmic puzzle, offering fragments that inform us not only about distant worlds, but also about our own planet's unique place in the universe, continually pushing the frontiers of our knowledge. Advances in quantum mechanics have had a profound effect on astrophysics, fundamentally altering how you might understand the universe. At its very heart, the field of quantum mechanics shows that particles exhibit the properties of both particles and waves, which introduces a degree of intricacy and unpredictability that classical physics was unable to account for. This dual nature influences the entire structure of the cosmos, shaping theories on everything from the birth of stars to the dynamics of black holes. One of the most crucial ways that quantum mechanics influences astrophysics is through the examination of stellar evolution. You see, stars produce their heat and energy via nuclear fusion, a process that depends on a phenomenon known as quantum tunneling, where particles can pass through energy barriers they should not be able to cross. This allows hydrogen nuclei to fuse into helium at temperatures far lower than classical physics would permit, which completely changes our models of how stars live and die, and deepens our knowledge of elemental creation. Furthermore, quantum mechanics is essential for comprehending phenomena like neutron stars and the properties of matter under the most extreme pressures. In such incredibly dense environments, the rules that govern quantum particles take precedence, giving astrophysicists a window into exotic states of matter. The relationship between gravity and quantum mechanics forms a conceptual bridge between the two great pillars of modern physics, presenting a possible key to a unified theory of the universe. Quantum mechanics also paves the way for new technologies that greatly improve astrophysical investigation. Innovations such as quantum imaging and quantum computing are creating new pathways for more advanced modeling and observation of cosmic events, permitting scientists to explore realms that were previously thought to be inaccessible. By weaving these quantum principles into their research, scientists are continuing to unravel the universe's deepest secrets, bringing together the microscopic and the cosmic in a beautiful scientific harmony. The Hubble Space Telescope, which you may know was launched in 1990, has dramatically reshaped our view of the cosmos. Among its most pivotal discoveries was the precise measurement of the universe's expansion rate, achieved by observing distant supernovae. This led to the astonishing revelation that the universe's expansion is actually accelerating, which in turn gave rise to the concept of dark energy, a mysterious force that seems to fill all of space and counteract gravity on a cosmic scale. Hubble has also provided unparalleled insight into the creation and development of galaxies. Its magnificent images showcase an incredible variety of galactic structures, from spiral galaxies much like our own Milky Way, to bizarre and irregularly shaped ones. By analyzing the composition and distribution of stars within them, you gain crucial knowledge about how galaxies merge and evolve over time, which are fundamental processes that shape the cosmic landscape we observe today. The telescope has also played an instrumental role in the study of exoplanets, which are planets that exist beyond our own solar system. The observations from the Hubble telescope have been instrumental in finding many of these remote worlds, enabling you to see analyses of their atmospheres and the habitable zones within different star systems. This work raises profound questions about life's potential in other cosmic corners. Furthermore, Hubble has delivered breathtaking images of distant phenomena like nebulae and black holes, which not only evoke a sense of wonder, but also help you understand the intricate processes that forge our universe. Each new piece of information adds another chapter to our cosmic history, serving as a reminder of the universe's sheer scale and complexity, and fueling your curiosity about what exists just beyond our vision. The exploration of our solar system's outer edges continues to be a captivating frontier for scientific inquiry, with several pivotal missions designed to expand what you know about this faraway region. Among the most awaited is NASA's Europa Clipper, slated for a 2024 launch. This mission will direct its focus toward Europa, Jupiter's ice-covered moon, which is thought to conceal a vast ocean beneath its frozen surface. You can understand why scientists are so focused on Europa. The potential presence of liquid water and essential chemical elements suggests it could be an environment capable of supporting life. The Clipper is tasked with performing a thorough survey of the Moon's ice shell and the ocean below to assess its composition and habitability. Another significant undertaking is the Jupiter Icy Moons Explorer, or JUICE, a mission by the European Space Agency that launched in 2023. The objective for JUICE is to study not just Europa, but also two of Jupiter's other fascinating moons, Ganymede and Callisto. You might find Ganymede particularly interesting, as it's the only moon in our solar system that generates its own magnetic field, a feature the mission will closely investigate alongside the moon's icy crusts and possible oceans. In addition, NASA's Dragonfly mission has captured your attention with its groundbreaking plan to explore Titan, Saturn's largest moon, with a launch scheduled for 2027. This craft aims to analyze Titan's dense atmosphere and its surface, which is marked by rivers and lakes of liquid methane and ethane. The goal is to comprehend the moon's prebiotic chemistry, making it one of the most ambitious missions ever to assess the life-bearing potential of an extraterrestrial world. Looking further ahead, you'll see active discussions and proposals for missions that could return to Uranus and Neptune, the ice giants of our solar system. These future endeavors might involve orbiters or landers, designed to solve the enduring mysteries surrounding their atmospheres, magnetic fields, and distinct weather patterns. With every mission, we get closer to answering fundamental questions about the solar system's origins and the possibility of life beyond Earth. Breakthroughs in artificial intelligence are fundamentally changing how you can approach the study of the cosmos. Astronomers traditionally had to manually comb through immense data sets, looking for patterns or irregularities that might signal a major discovery. Now, as you are inundated with a torrent of information from telescopes and cosmic signals, AI can analyze this data with a level of speed and accuracy that was previously unimaginable. Machine learning algorithms can be trained to spot features in cosmic data that would be easy for the human eye to miss, giving you a powerful new tool. For instance, they can pinpoint unusual fluctuations in the light from distant stars, which could signify the existence of an exoplanet or an entirely new kind of celestial object. This capability not only makes the process of discovery faster, but also expands the range of what researchers can search for. Another incredible aspect of AI in this field is its capacity to manage and interpret information from many different sources at once. You have large-scale projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, which will produce petabytes of data. AI can assist in classifying this information in real time, helping astronomers identify transient events like supernovae or gravitational waves, thereby deepening your understanding of the universe's most dynamic events. Building new observatories is absolutely vital in your ongoing endeavor to solve the universe's greatest riddles. As our technology improves, so does your ability to observe celestial events that were once completely out of reach. Each new observatory serves as a more powerful eye on the cosmos, allowing scientists to collect crucial data on stars, galaxies, and even the enigmatic dark matter that constitutes most of the universe's mass. A key benefit of constructing these new facilities lies in the advancement of their observational technology. You'll find them equipped with cutting-edge instruments that can detect wavelengths of light far beyond the range of older telescopes. This allows you to explore the universe in infrared, ultraviolet, and radio waves, uncovering structures and processes, such as the birth of stars and the mysterious energy driving cosmic expansion, that you are only just beginning to comprehend. to capture the clearest possible views of the cosmos. Observatories are often constructed in remote locations, like high-altitude mountaintops or arid deserts. These pristine environments minimize distortions from atmospheric turbulence and the obscuring effects of light pollution, enabling astronomers to gather sharper images and more precise data. This clarity is fundamental to advancing our comprehension of the universe's grand structure and evolution. Moreover, each new observatory becomes a global hub for scientific cooperation, attracting researchers from across the world. This convergence of diverse expertise and fresh perspectives cultivates innovation and drives significant breakthroughs. Through shared discoveries and collaborative observation, these scientific communities work together toward the common objective of solving cosmic mysteries and expanding the frontiers of human knowledge. The advent of commercial spaceflight is poised to dramatically expand our capacity for exploring celestial bodies. For the first time, space travel is becoming accessible to a broader demographic. And as more private firms join the effort, we can expect a more diverse cohort of spacefarers. This democratization of space promises to introduce new ideas and unconventional thinking into the field of cosmic exploration, potentially leading to revolutionary scientific insights. In addition, the growth of space tourism serves as a powerful engine for technological progress. The challenge of building spacecraft to transport private citizens safely necessitates the development of superior technologies, which can then be adapted for scientific missions. Commercial companies are driven to innovate more efficient propulsion, life support, and landing systems. Advancements that not only improve our ability to explore, but also bring us closer to solving the profound mysteries beyond our world. This heightened public engagement with space can also spur greater interest and secure more funding for scientific research missions. As the prospect of visiting space captivates more people, the appetite for knowledge about our universe is likely to grow, encouraging both governments and corporations to invest more heavily in missions to the Moon, Mars, and other worlds. These partnerships between private enterprise and scientific institutions create a synergistic approach, sharing resources and knowledge to unlock a deeper understanding of the cosmos with every launch. As humanity continues to gaze upward, the dream of traveling between the stars captivates the collective imagination more than ever, with several remarkable technologies emerging to make it a potential reality. One of the most compelling concepts is the use of light sails, which would be propelled through space by powerful ground-based lasers. A small spacecraft equipped with such a sail could achieve immense speeds over time, bringing the nearest stars within the reach of a human lifetime. Another fascinating area of research is nuclear propulsion, where scientists are exploring the power of nuclear fusion, the same process that fuels our sun, to drive spacecraft. A vessel powered by a fusion rocket could theoretically generate enough thrust for rapid transit to distant solar systems, drastically cutting down the journey times of conventional methods. An even more exotic idea involves antimatter, which annihilates on contact with normal matter to release an incredible amount of energy, potentially enabling travel at near light speeds, though the challenges of producing and containing it remain immense. Finally, the role of advanced robotics and artificial intelligence will be absolutely critical for any future interstellar missions. These intelligent systems will be essential for navigating uncharted territory, conducting vital scientific research, and making autonomous decisions light years away from human guidance. With these innovations on the horizon, the long-held dream of visiting other star systems is steadily transitioning from science fiction to scientific fact. The next generation of telescopes is set to revolutionize our understanding of exoplanets, providing unprecedented details about worlds beyond our solar system. Equipped with cutting-edge instrumentation, these observatories will allow astronomers to study the atmospheres of these distant planets with extraordinary precision. By analyzing the light that passes through an exoplanet's atmosphere, scientists can decode its chemical composition and identify clues about its potential habitability. A primary goal will be the detection of biosignatures, indicators that could signal the presence of life. Future telescopes will be powerful enough to identify atmospheric gases like oxygen, methane, and carbon dioxide, which may be produced by biological processes. Discovering these gases would allow us to investigate the conditions necessary for life as we understand it, bringing us closer to answering whether we are truly alone in the universe. Another transformative capability of these new instruments will be their power to capture direct images of exoplanets. Current observatories often find it difficult to see these faint planets against the brilliant glare of their parent stars. However, by employing advanced techniques such as coronagraphy and interferometry, astronomers will be able to filter out that starlight and obtain actual photographs of these remote worlds for the first time. This detailed visual information allows scientists to more deeply investigate the atmospheric properties and surfaces of these distant worlds, yielding fresh insights into their variety and fundamental characteristics. As our technological capabilities grow, our entire perception of the cosmos is poised for a dramatic transformation. Each successive advancement promises thrilling new discoveries, with the growing possibility of finding other exoplanets, perhaps some very similar to our own, powerfully stoking our curiosity and pushing us closer to answering the ultimate questions of our cosmic significance and the existence of other life forms. International cooperation in the field of space exploration has been absolutely vital for pushing the limits of what we know about the universe, bringing together the financial resources, intellectual capital, and unique skills of scientists from across the globe. By working in unison, they can overcome challenges that would be simply insurmountable for any single nation acting alone. These joint ventures merge a wide array of expertise and cultural viewpoints, which in turn cultivates highly creative solutions to incredibly complex problems, as perfectly demonstrated by the successful partnership behind the International Space Station, or ISS. Among the most significant advantages of these global alliances is the ability to pool costs and share specialized knowledge. When several nations contribute to a single project, the immense financial weight is distributed, transforming ambitious undertakings from impossible dreams into feasible realities. This framework also allows countries with developing space programs to benefit from the advanced technologies and experience of their partners, an exchange that not only speeds up the pace of discovery, but also enables scientific breakthroughs that would otherwise remain out of reach. Furthermore, this kind of teamwork cultivates a rich environment for scientific investigation, as researchers from different backgrounds can analyze challenges from entirely new angles. This intellectual diversity often sparks original hypotheses and innovative research strategies, significantly boosting the overall effectiveness of the mission. For instance, collaborative missions to Mars have produced results that have profoundly altered our understanding of the planet, including crucial evidence that liquid water once flowed on its surface, a discovery directly tied to the search for life beyond Earth. Shared scientific objectives also have the power to foster peaceful global relationships and a profound sense of unity. The common pursuit of knowledge transcends political boundaries, nurturing a feeling of a connected global community. Discoveries made by instruments like the Hubble Space Telescope have not only broadened our cosmic horizons, but have also united the world's scientific community, showing how cooperation can inspire humanity to look past its differences. This effort is more than just launching hardware into space. It is a representation of our species' collective drive to explore and comprehend the universe we call home. The moons that orbit Jupiter and Saturn present an incredible wealth of potential for scientific breakthroughs, largely because they are such varied and compelling worlds that could possess the very conditions required for life. Among the most tantalizing of these is Europa, a major moon of Jupiter, which is believed to hide a colossal ocean of liquid water beneath its thick, icy shell. Through the study of Europa, researchers aim to uncover evidence of microbial life, while also learning more about the moon's geology and the chemical reactions taking place in its hidden ocean. Similarly, Saturn's moon Enceladus captures scientific interest with its spectacular geysers, which eject plumes of water vapor and complex organic molecules directly into space. The existence of these jets is strong evidence for a subsurface ocean concealed by the moon's frozen exterior, and a chemical analysis of these emissions could offer direct clues about its habitability. The discovery of life, or even just its essential components on any of these moons, would fundamentally reshape our understanding of biology and its capacity to thrive in extreme conditions. The sheer variety among the other moons in these systems provides even more unique research opportunities that could lead to revolutionary findings. For example, Ganymede, the largest moon in our solar system, generates its own magnetic field, while Saturn's largest moon, Titan, is home to vast lakes of liquid methane. Each of these celestial bodies offers a distinct environment for investigating planetary formation, atmospheric dynamics, and the different pathways that could potentially lead to life, enriching our knowledge with every new mission. Though it remains entirely in the realm of theory, the idea of time travel presents a host of captivating possibilities for investigating cosmic mysteries. Just consider the ability to venture into the distant past to observe firsthand the formation of the universe, or the birth of the very first stars. Witnessing these pivotal events directly could offer unmatched insights into how cosmic anomalies, such as black holes or the remnants of a supernova, have developed over billions of years. In principle, traveling through time would permit scientists to collect incredibly detailed data from moments that are otherwise lost to history, such as the specifics of galactic collisions, or the behavior of dark matter throughout different eras of the cosmos. By observing the direct evolution of these phenomena, researchers could significantly refine their current models and theories, potentially unlocking some of the most profound secrets the universe holds. Time travel could also provide a unique vantage point on the origins of these cosmic irregularities. A journey to the earliest moments of the universe, for example, might allow us to encounter primordial black holes or watch the initial stars ignite. This would enable us to draw a direct line between the anomalies we observe today and their ancient origins, greatly deepening our comprehension of universal evolution. For now, however, all of these possibilities remain purely speculative. The very idea of time travel presents us with paradoxes that seem to defy our current understanding of physics. Nevertheless, exploring these concepts can ignite your imagination and inspire new lines of inquiry in cosmology, prompting you to consider how the fundamental mysteries of time and space might be interwoven in ways we have yet to comprehend. As humanity approaches the threshold of interplanetary settlement, with Mars as a primary target, we must confront significant ethical dilemmas. A major concern is the potential harm we could cause to any pre-existing ecosystems, Colonizing another world carries the risk of inadvertently destroying microbial life or unique environmental niches, echoing the impact early explorers had on Earth's indigenous peoples and ecologies, and forcing us to question our duty to protect alien life, no matter how simple. Beyond environmental impact lies the complex issue of ownership and the entitlement to settle other worlds. Is it justifiable for any single nation or entity to lay claim to a celestial body? The Outer Space Treaty of 1967 provides a foundational guideline, stating that space should be for the benefit of all humanity and prohibiting any country from claiming sovereignty. Yet, with private corporations now entering the space race, establishing property rights and rules for resource extraction could ignite conflicts similar to historical colonialism. Furthermore, we must carefully consider the logistics of human habitation itself. Establishing a colony on another planet brings up profound questions about governance, social organization, and the welfare of its inhabitants. It is crucial to determine how we can guarantee that a new off-world society embodies ethical principles and provides respect for everyone. We need to establish foundational rules to prevent potential problems, from environmental destruction to social inequality among the settlers. Ultimately, as you contemplate humanity taking its first steps onto another planet, it is essential that we draw lessons from our own past. Our expansion into the cosmos should be guided by principles of respect and justice. This will help ensure a future where space exploration not only broadens our cosmic perspective, but also honors the delicate balance of life, wherever we might discover it. The questions you ask now will define our interplanetary future and set the ethical standards for generations to follow. Scientists delineate a habitable zone as the specific region orbiting a star where conditions could be just right for life as we understand it. This area is often called the Goldilocks zone because it is neither excessively hot nor overly cold. The critical variable is the planet's distance from its star, which determines whether liquid water can exist on the surface. If a planet is too close, its water will vaporize, and if it is too distant, all water will be locked away as ice. The precise location of a habitable zone is directly linked to the luminosity and category of its star. For instance, the habitable region around a smaller, cooler star like a red dwarf would be situated much closer than the one surrounding a larger, hotter star such as our Sun. Researchers have also determined that these zones aren't limited to planets like our own. Exoplanets are also considered potentially habitable if they fall within these favorable orbital distances. However, there are fascinating exceptions within these zones, as not every planet situated in a habitable region is guaranteed to support life. A planet might suffer from extreme weather patterns, be devoid of a protective atmosphere, or endure intense stellar radiation. Venus and Earth, which are both inside our Sun's habitable zone, offer a stark contrast. While our planet thrives with life, Venus stands as a warning with its dense, poisonous atmosphere and a catastrophic runaway greenhouse effect. Researchers are continuously refining what it means to be in a habitable zone by incorporating additional factors, such as a planet's atmospheric makeup, the stability of its climate, and the strength of its magnetic field. As our technology becomes more sophisticated, astronomers are getting better at pinpointing exoplanets within these promising celestial territories, leaving you to wonder what kinds of civilizations or ecosystems might be concealed in the vastness of space. Many are captivated by the possibility of extraterrestrial life, with proponents arguing that the sheer scale of the universe makes its existence highly probable. With billions of galaxies, each hosting billions of stars, many of which likely have planets in habitable zones, it seems statistically unlikely that Earth is the only place where life has emerged. Discoveries in our own solar system have only deepened this curiosity, such as the subsurface oceans on Jupiter's moon Europa, and evidence of briny lakes on Mars, which suggest environments where microbes could potentially survive. Skeptics, however, raise powerful counterarguments, with the Fermi paradox at the core of their position. This paradox poses a simple question. If extraterrestrial civilizations are so likely, why have we found no proof of their existence? Decades of searching through programs like the Search for Extraterrestrial Intelligence, or SETI, have yielded no confirmed signals or contacts. This profound silence leads some to doubt that advanced communicative life is out there. Additionally, some scientists propose that the biological and geological conditions on Earth are extraordinarily rare. They argue that everything from our planet's stable climate to the abundant presence of water represents an exceptional combination of circumstances. If life is as fragile as this perspective suggests, then intelligent civilizations might be exceedingly uncommon or fleeting. While simple microbial life could be common, complex beings capable of interstellar communication may be one of the rarest things in the cosmos, keeping this debate dynamic and full of mystery. Remarkable organisms known as extremophiles manage to flourish in the most hostile places on Earth, from the scalding water of hot springs to frozen ice sheets and deep ocean hydrothermal vents. The existence of these hardy life forms has dramatically broadened our concept of what makes an environment habitable. Previously, scientists held the belief that life required very narrow, temperate, and bountiful conditions. The discovery of extremophiles has overturned this view, demonstrating that life can not only endure, but actually prosper under extreme circumstances. This realization carries profound weight for astrobiology, the field dedicated to studying life's potential beyond our world. If life on our own planet can thrive in such severe settings, it opens up the possibility that life could exist on other planets and moons we once deemed inhospitable. For instance, celestial bodies like Europa, with its icy crust covering a deep ocean, or Enceladus, which ejects water geysers into space, have become leading candidates in the search for extraterrestrial organisms. Furthermore, the capacity of extremophiles to tolerate intense radiation, immense pressure, and extreme temperatures challenges our very definitions of life's resilience. By investigating how these organisms withstand such punishing conditions, scientists can refine their understanding of life's potential in environments formerly considered uninhabitable. Researchers have even pinpointed specific genes that grant extremophiles their resistance to radiation, offering crucial insights that not only define the boundaries of life on Earth, but also direct our methods for searching for it elsewhere. In essence, extremophiles have enlarged both our definition of what life can be and the variety of environments capable of supporting it. As we push our exploration further into the solar system and beyond, these minuscule yet incredibly tough organisms serve as a constant reminder of nature's astonishing adaptability and the countless forms that life might take throughout the universe. The ongoing study of these creatures fuels the exciting possibility that we are not alone. Recent revelations concerning the atmospheres of exoplanets have ignited tremendous excitement within the scientific community, hinting at the potential for life far beyond our solar system. Technological breakthroughs, especially with advanced space telescopes, have empowered astronomers to collect vital data about these remote worlds. In particular, the James Webb Space Telescope has delivered unparalleled insights into the atmospheric makeup of exoplanets, uncovering complex gaseous structures that might be able to sustain life. Among the most electrifying findings is the detection of water vapor in the atmospheres of multiple exoplanets, a critical signpost, since water is fundamental to life as we understand it. Investigators have also identified traces of carbon dioxide and methane, which are compelling because they could be tied to biological activity. The presence of these gases in particular combinations could point toward microbial life, operating in ways similar to what we see on Earth. Moreover, some research points to the existence of atmospheres that could maintain temperature ranges favorable for life. Worlds situated in the habitable zones of their stars, where conditions might permit liquid water to persist, are of special interest to researchers. The discovery of chemical diversity in these atmospheres, including the potential for organic compounds, makes you wonder about the kinds of life that could arise in environments so different from our own. With every new observation of an exoplanetary atmosphere, we edge closer to resolving the ancient question of whether we are truly alone in the cosmos. Each discovery inspires a profound sense of awe and possibility, as scientists not only uncover the potential for life, but also the countless ways it could emerge on planets orbiting distant stars. These ongoing inquiries are not just deepening our comprehension of the universe, they are fundamentally reshaping what it means for a world to be considered habitable. While isotopic signatures found in meteorites offer us cosmic clues that guide the scientific search for life beyond our planet, we are met with an enigmatic silence from the cosmos. This quiet has spurred scientists and thinkers to put forward several compelling theories. A prominent explanation is the rare earth hypothesis, which posits that the precise circumstances needed for complex life to arise are exceedingly uncommon. Although simple microbial life might be abundant, the unique confluence of factors, like a stable parent star, ideal planetary conditions, and a protective magnetic field, may be an extraordinary cosmic fluke. Another hypothesis relates to the self-destruction of technologically advanced civilizations. This idea proposes that societies inevitably face existential threats like nuclear conflict, catastrophic climate change, or uncontrollable pandemics at a certain point in their development, and ultimately fail to overcome them. The Great Silence could simply be the result of most intelligent species either wiping themselves out or never reaching a stage of advanced technological capability. It is a sobering thought. Additionally, some scientists theorize that advanced civilizations might deliberately conceal their existence. This concept is closely related to the zoo hypothesis, which suggests that other intelligent species choose to avoid contact with us, much like zookeepers who observe animals without disturbing their natural habitat. They might be studying us from a distance, or have ethical principles that forbid them from interfering. These theories underscore the immense complexity of the universe and our uncertain place within it. Ultimately, these ideas compel us to ask whether humanity is genuinely alone, or just a small part of a much quieter cosmos. To help quantify these possibilities, we can turn to the Drake equation. This is a fascinating probabilistic tool, first proposed by the astronomer Frank Drake in 1961, which is used to estimate the number of advanced civilizations in our galaxy with whom communication might be possible. The equation breaks down this grand question by incorporating several key factors that reflect the conditions necessary for intelligent life to emerge. The Drake equation functions by multiplying a series of probabilities, including factors like the speed of star creation and the percentage of those stars that have planets, to estimate the number of advanced societies in our galaxy. Its true value, however, extends beyond just yielding a number. It serves as a powerful catalyst for scientific debate on the hunt for alien life. By dissecting the intricate requirements for life into more manageable parts, the equation allows scientists to pinpoint what we know and, more importantly, what we still need to learn. This approach fuels new research in diverse fields from astronomy to biology, and has inspired ambitious projects like SETI, the Search for Extraterrestrial Intelligence, which uses radio telescopes to listen for communications from potential civilizations, with every finding helping to fine-tune our cosmic calculations. Researchers have come across several captivating signals that some speculate could be signs of extraterrestrial intelligence. Perhaps the most well-known is the WOW signal, which astronomer Jerry Eman detected in 1977 at Ohio's Big Ear radio telescope. Lasting for a full 72 seconds, this intense, narrow-frequency radio transmission appeared to originate from the Sagittarius constellation, yet its source remains a complete mystery. Another compelling case involves fast radio bursts, or FRBs, incredibly brief events that unleash the same amount of energy our sun produces in a full day. While many are linked to natural sources like magnetars, the debate continues over whether some could be artificially generated. In the 1960s, the LGM signals also caused a stir, with a name short for Little Green Men, that reflected the discoverer's initial playful speculation. These signals were later identified as the emissions from pulsars, which are rapidly spinning neutron stars. The search isn't limited to radio waves. In 2017, the star KIC 8462852, nicknamed Tabby's star, showed bizarre and irregular dips in brightness, leading to theories about alien megastructures, though subsequent research has pointed toward more mundane causes. Each of these cosmic puzzles serves as a potent reminder of how much remains unknown, continually pushing us to explore the vast possibilities of the universe. Investigating interstellar microbes provides a fascinating perspective on the very origins of life, as the discovery of these organisms surviving in the vacuum of space poses fundamental questions about life's tenacity. If life can withstand such extreme environments, it strongly implies that its presence in the cosmos could be far more common than you might imagine. This leads directly to the captivating theory of panspermia, which proposes that life can be transported across space on meteorites or comets. The idea that hardy microbes could journey between worlds and initiate life elsewhere forces us to reevaluate our own origins, suggesting life on our planet may not have been a singular miracle, but part of an ongoing universal process. By examining how these organisms endure such punishing conditions, we gain crucial clues about the essential ingredients for life to flourish elsewhere. Analyzing their genetic makeup and metabolic functions helps us identify the kinds of extraterrestrial settings that could support similar life forms, allowing astrobiologists to strategically select targets for future missions. Ultimately, these interstellar microbes force us to expand our definition of life, pointing to the possibility that it is not a rare terrestrial exception, but a common cosmic occurrence, deepening our understanding of life's emergence not just on Earth, but potentially throughout the universe. Among the most promising locations in our solar system for finding extraterrestrial life is Europa, one of Jupiter's moons. Its most remarkable quality is a massive, planet-wide ocean hidden beneath a thick crust of ice. An ocean that could hold more liquid water than all of Earth's oceans combined. The existence of this much liquid water already makes it a top priority for exploration. What elevates its potential even further is the strong possibility that this ocean directly interacts with the moon's rocky mantle, a scenario that could provide the precise chemical energy and nutrients required to support living organisms. The discovery of life in Earth's most severe conditions fuels the compelling question of whether comparable organisms might flourish within Europa's concealed ocean. This moon, a prime candidate for habitability, continues to captivate our scientific curiosity, driving the search for answers about life's existence beyond our world. When you consider the sheer scale of the universe, proponents of extraterrestrial life believe its existence is a matter of high probability, pointing to the billions of stars in the Milky Way alone, many with planets in habitable zones where conditions could be just right. Jupiter's moon, Europa, is a particularly captivating target because its subsurface ocean brings to mind Earth's own deep-sea hydrothermal vents, where ecosystems thrive without any sunlight. The potential interaction between Europa's liquid ocean and its rocky mantle could yield a nutrient-rich brew, creating the ideal conditions for the chemical evolution that life requires. These factors make Europa one of the most promising places in our solar system to search for life. Another telling clue about Europa is its remarkably young surface, which is covered in long cracks and ridges. These formations strongly suggest ongoing geological activity, meaning the icy crust is constantly being renewed. This process could be crucial for transporting energy and nutrients from the ocean below to the surface, possibly generating an environment capable of sustaining life. Furthermore, Europa's tenuous atmosphere, which is composed mainly of oxygen, hints at complex processes that might link the surface with the deep ocean beneath it. To investigate these possibilities further, scientists are preparing ambitious missions in the coming years, including the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, and NASA's Europa Clipper. The primary goal of these endeavors is to collect more definitive evidence about this intriguing moon. Each new piece of data gathered could illuminate Europa's potential as a cradle for extraterrestrial organisms and offer profound new perspectives on our cosmic neighborhood. Our own galaxy, the Milky Way, has a stunning structure that continues to fascinate researchers. At its very heart, there is a central bulge made up mostly of ancient stars, which encircles a supermassive black hole named Sagittarius A star. This incredibly dense core is the gravitational anchor that dictates much of the galaxy's overall motion and behavior. Spreading out from this center is a vast rotating disk that holds the majority of the galaxy's young stars, gas, and dust, serving as the primary site for new star formation. Extending from the central disk are the magnificent spiral arms of the Milky Way, which create the iconic pinwheel pattern you can observe from Earth. These arms are not rigid fixtures, but are instead dynamic waves of matter filled with young, intensely hot stars and vibrant nebulae where stellar birth is rampant. These regions showcase an incredible diversity of stellar phenomena, with their bright, youthful stars serving as some of the most prominent beacons of light in our galaxy. Enveloping the entire visible galaxy is the galactic halo, a far more diffuse and enigmatic region. The halo is sparsely populated with old stars and globular clusters, which are dense, spherical collections of ancient stars. More importantly, This area is thought to contain a vast amount of dark matter, an invisible substance whose gravitational pull is essential for shaping the galaxy's structure and holding it all together. In fact, dark matter is believed to make up most of the Milky Way's mass, profoundly influencing the orbits of stars. Beyond its physical structure, the Milky Way's chemical makeup is a rich tapestry, woven over billions of years of stellar life and death. Heavier elements like carbon and oxygen, forged inside stars, are continuously scattered across the galaxy. When massive stars end their lives in supernova explosions, they enrich the cosmic environment with these vital materials, fueling the next cycle of star and planet formation. This perpetual process creates a dynamic cosmic ecosystem, influencing everything from the birth of stars to the potential for life on other worlds. Globular clusters represent a profound puzzle that challenges our standard models of how galaxies are built. These celestial objects are tightly packed, spherical swarms of thousands or even millions of stars that orbit the centers of galaxies. What makes them so remarkable is their incredible age and density, as most globular clusters are between 12 and 13 billion years old, placing them among the most ancient objects known in the universe. Conventional theories suggest that galaxies form incrementally, by merging with and absorbing smaller celestial structures over immense spans of time. Within this framework, you would expect to find a mixture of star clusters with varying ages. The existence of these uniformly ancient globular clusters, however, complicates this picture, prompting us to reconsider the very processes that governed the formation of galaxies and stars in the early universe, and fueling new avenues of cosmic investigation.